Okay, Sepideh, over to you. Sepideh's an old friend to Delta. I think I met her at my first Delta in Rotorua. Unfortunately, she couldn't come to Brisbane this time, but we're looking forward to your talk, Sepideh, and hopefully Caleb is with you. We can see your screen there, so we'll hand over to you. I'll try and get your
Hi,
sorry.
thanks. Thanks so much. Hi, everyone. I'm Sepideh Stewart, and Caleb is my co-presenter, and also Caleb is my PhD doctoral student. So I'm just trying to get this slides on a full. So I just have to move my Zoom a little bit out of the way. Sorry. Don't think I can do that. Let me see. This was working before. Now let's see. Can you guys see this, my slides, or do you want it? I got it. I
Yeah.
think I got it. Okay, sorry.
Try single page, Paul says.
Okay, I think I got it. How's this?
Beautiful. Okay. Over to you.
All right,
Welcome,
great.
Sepideh.
Thank you so much. Yeah, I'm sorry I couldn't be at Delta this year. According to Michael's list, I think this would have been my ninth Delta. So, so it was thanks for putting that list out on the first day. So just a quick overview of this is a research study about an abstract linear algebra proof course. The theoretical framework, some of you are familiar with this, is on instrumental genesis and Vergnaud's schemes. We'll talk about analysis of one student's MATLAB code and proof and survey responses of the whole class. So some of you are familiar with the literature on linear algebra. So linear algebra is a key topic. Of course, you are teaching it, so you are familiar with mathematics of it. That many mathematics majors and other fields take linear algebra. I was teaching abstract linear algebra. This is a second course in my department, which is based on proof. So I collaborated with two colleagues from MathWorks, Mike Michaelides and Armando Garcia, to redesign my course and include some labs and projects and using MATLAB. So they were from MATLAB, but their job was basically as educators. So there are these special people that help the instructors, which I did not know that before. So my goal was to help students explore programming and applications of linear algebra inside this abstract course, and I wanted to basically make some contributions in bridging between theoretical and practical thinking. So my education was in Auckland, University of Auckland, and in Auckland many years ago when I was an undergraduate, I always felt like we had labs. We used to have assignments. They had MATLAB or Maple components, and we would go to the lab and we will work on those. And when I came to my university in Oklahoma, I felt like my students don't have what I had all those years ago. So it was really sad for me. Of course, in those days when I was a student in Auckland, we didn't have much resources. The only resource we had, some of you remember that it was a book, MATLAB book, which was chained to the on the table in the room. This beautiful lab, but not many MATLAB resources. So interesting contrast. That was my motivation. Some of you are familiar with literature, education literature of linear algebra, and Anna Saprinska was one of the pioneers who looked into students' struggles with linear algebra. She observed that many students are more comfortable with the practical aspects of the subject, especially computation, and find reading mathematics difficult and tend to limit the reading to examples and exercises. So she was basically concerned and she was calling for maybe we should utilize applications, maybe we should look at computations and even numerical aspects. But she wasn't saying that we should throw away the theoretical thinking. This idea here in this slide, it really goes well with Jess's plenary a couple of days ago that she talks about rigor. So proof is basically the ultimate rigor. But interestingly, recently, that environment and that landscape is changing, and technology is coming into that, and something that maybe these authors, Hannah and her colleagues, are saying that maybe this is something we did not expect before. That proof would be so resistant to technology changes that are happening around us. This other one by Bayer et al. This is a long list of authors that wrote this about proof and how the landscape is changing. Now maybe the time to reconcile theory and practice. It means precision and intuition through the advent of computer proof assistance. So if you look at the latest of IMS, the notices this year alone, you'll find a lot of papers that are talking about proof assistance and how the technology is working. Mathematicians are working with technology to do proof validations, which is really fascinating to me. So I went to ATCM, which is the Asian Technology Conference. Some of you are familiar with that conference, and I learned about computational thinking last year. So why bringing computational thinking into a classroom? I knew the value of that because as a student, I experienced it. So these authors are saying that this gives learners a more realistic view of what these fields are, better prepares the student for pursuing careers in these disciplines, and make them more savvy STEM citizens of the future. Actually, this is by Weintraub. I have the list of the references I'll show you later. So my study was about, as I said, I was teaching this abstract linear algebra, which is the second course in the spring of 2024. And the content is a lot of like second course materials that was in there. And I was using the textbook by Sheldon Axler, Linear Algebra Done Right. I had 22 students enrolled, 18 undergraduate and 4 graduate. These are, we call them slash listed. That means graduates can participate, can also enroll. 15 students participated in this study. And assessment was, so I gave them assignments, 6 labs, and class activities and midterm test. And the rest was I kept everything almost the same. Except I added these 6 labs and a project. And for fun, for these 6 labs, I said that one of these labs I want to design it myself. And for fun, I chose one of Axler's proofs, and I said, this looks like a good one because this looks like algorithmic enough. Maybe a student can actually code this. So the proof, the theorem is every spanning list in a vector space can be reduced to a basis of the vector. And he goes through like the steps, like step 1, if V1 is 0 vector, delete it from the set B. And if it's not, keep it. And then step K is if VK is in the span of this V1 to VK minus 1, then delete VK because it's redundant. And if VK is not in this, then leave it unchanged. And he uses the idea of a dependence lemma, so proof goes a little bit longer here, but I thought this would be a nice one for students to try. Now comes to my framework, instrumental genesis. According to Trush, so we use this framework to basically try to explain what is going on with the data. So this frame leads us to clarify our initial definition. Instrumentation is the action by which a subject requires an artifact, and the effect of this action on the subject who develops from this artifact an instrument for performing a task. An instrument is thus made of of an artifact component and a cognitive component. Trish clarifies that instrument is here defined as a mixed entity composed of a part of an artifact and a scheme. So I'm going to talk a little bit about the scheme in a minute. Then Sinclair and her colleagues talk about this artifact does not intervene in a neutral way in teaching learning. It carries its own techniques, instrumental knowledge, signs, and meanings, and so on. So it's really fascinating, this study. So we looked at schemes of Vergnaux's schemes. I don't know why I never actually looked at this paper before in depth until we read the paper by Goudet and her colleagues, and we thought, wow, this is an amazing framework, and we need to really look into that. So Vergnaud describes these four aspects: intentional aspect, like it involves a goal or sub goals in your developing your sub goals and anticipations. Generative aspect, when it involves rules like sequence of actions, information gathering, and controls. This control also is from like heuristics and controls that Schoenfeld talks about too. Epistemic aspect of schemes, that's mostly concepts and theorems, and the computational aspect. So here's a picture of the instrumental genesis. Maybe you can see that a little bit more in action, that how you have an artifact and your subject and instrument do something, part of the artifact plus the schemes. This is something that I never really realized until recently. So here's our initial, I say initial because Caleb and I are still working on this. So this is based on a conference paper that we said, what was the nature of instrumentation of programming with MATLAB in the production of linear algebra proof? So I'm going to hand it over to Caleb.
Hello. So this portion is actually our transcription of student one's code for a part of what they submitted in lab two. So this is what they constructed in MATLAB that was meant to validate the linear dependence lemma 2.19. Now, before this portion of code, they actually wrote a paragraph explaining their intentions for their code, their own understanding, and they go on to claim that not only does this code, as designed, validate 2.19, the linear dependence lemma. They also believe it validates the theorem 2.30, the proof that we had just looked at. So the design for this, again, the linear dependence lemma is a statement that removing a linearly dependent vector from a list does not change the span of that list. So that's kind of ultimately what they were, like the big umbrella of what they were trying to do with this code, but also believe that it proved the theorem or validated the theorem at the same time. So before this, they constructed a linear dependent list of vectors, and then we hit this portion of the code. And so they have a while loop that says just while true. So this is going to keep going until somehow we break out of this code. So in the syntax here, their vectors exist as columns of this matrix that they're looking at. And so they're going to choose a random vector in the list and remove it and see if removing that vector changes the rank of the list of vectors. If it does not change the rank, that would mean that it must be linearly dependent with respect to the rest of the list. So go ahead and remove that. Ultimately trying to construct a list without the linear dependent vectors. Now, because this is an if-else statement here, if removing the rank does change, or removing the vector does change the rank, then instead increment their charge counter, or sorry, change counter as they have it. And they're going, and then at the end of that sequence, they have a statement, an if statement. If the change counter reaches max iterations, value that they've declared before this portion of the code, then break out of this while loop. So the very interesting part of this code is that, for one, it doesn't look exactly like Axler's proof, right? So this is supposed to be their validation for 2.19, but again, in their own words, they also see this as a validation of theorem 2.30. That you can reduce this linear dependent, or you can reduce a spanning list to a basis. Now, what's interesting about this is that their check for if you can remove a vector or if that vector would be linearly dependent is whether or not it changes the rank. Now, that already assumes the linear dependence lemma, so this really functions a lot more as a validation for the theorem than it does for the lemma. But also because this is a random vector that it tries to remove every time, there's no guarantee that they're picking the right vectors to remove. In theory, the computer could keep trying to remove the first vector, so there's not a wonderful guarantee here. Now, very interestingly, if we look at their proof for this theorem from the exam, we have their transcription here. And so they make this statement, every spanning list in a vector space can be reduced to a basis of the vector space as what they're trying to prove. That's theorem 2.30. And then they start out by supposing that you have a spanning list of your vector space. And they make a very interesting side note to themselves. We have tried reducing as the length of a linear dependent or linearly independent list must be less than or equal to the length of a spanning set. So to make a linearly independent list of vectors, you need to remove them rather than adding. So they're starting with a spanning set, so they're trying to bring that length down to the length of a linearly independent list. So not directly a part of their proof, but a side note to themselves, reminding them what they're supposed to do here. Then using the linear dependence lemma, we look for vk, the smallest k, where vk is in the span of the previous vectors. If there is such a vector, remove vk. As the lemma states, the remaining vectors after vk is removed will still span the same vector space as the original list. So repeat this step until it doesn't apply, and you end up with a list of linearly independent vectors that still span. And so then claiming that this means it meets the definition of a basis. Now, the very interesting note here is that the part of Axler's proof that they miss is the test if the first vector is the zero vector or not. They don't check that. They don't include that. And that's kind of the same piece that's missing from the code that they had before. Now we can look at the schemes that we see as as the student schemes, we look at the aspects internal to those. And so we think that these are the aspects that are displayed through the proof and the code. The epistemic aspect, their understanding of the concepts at hand, we see that there's a really tight connection between span and the rank of a list. They really connect the lemma and theorem 2.30, believing even that their code that's in their mind validating 2.19 also validates the theorem at hand. Their intentional aspect, again, they wrote a paragraph describing their plans for their code, so they fully displayed that. And also they have wonderful comments all throughout their code, as you saw before, that make clear what their intentions are at every step. And their computational aspect we see in how they construct the linearly dependent list, because in order to validate this theorem, they have to have a linearly dependent list of vectors, and that's a very non-trivial part. And so how they can create that, we believe, relates to their computational aspect. And this student actually randomized a dimension, created like the typical basis that you would see, and then chose a random number of vectors to add and randomized scalars in order to create a linear combination to guarantee that those new vectors would be linearly dependent. So they really displayed these aspects very clearly with their code and their proof, we believe. Now, these students responded to a survey that was given at the end of class with very interesting notes here. And so 4 of them actually said, out of the 13 that we're analyzing in total, 4 of them said that they were familiar with MATLAB before this course. When asked if they had done any programming and if their knowledge of coding improved as a part of this course, 12 of them said yes to both. When asked if their knowledge of linear algebra increased because of the coding associated with its class, or if the applications helped them learn more linear algebra, only 1 said no, but all of the other 12 responses said that it did help them build connections and understanding for the theorems and the definitions, having to create those applications. Now, they also saw coding in the future as being very important, while unsurprisingly being influenced by AI. And they also believe that this linear algebra course prepared the students across various disciplines for their futures, whether just helping with their mathematical abilities or supporting them in their degree of interest. And they also had widely favorites among the labs. So when asked of what their favorite labs was, a majority of them claimed Lab 6. Some of them said Lab 5, but they were very passionate in their answers, so very meaningfully engaged with the students, it seems.
All right, thanks so much, Caleb. So nobody basically said this lab, right? No one said that this lab was their favorite. I think one student said that it helped because I gave the same theorem and proof in the midterm test, and I wanted to see how much they actually retained because of coding. Did it affect them? So one student wrote that that really helped, but others did not comment much. But going back to student one again, the student one was very interesting because she was very engaged and she was a computer engineer student at the time. She said that I can't describe the satisfaction I had after seeing how these abstract concepts are so engraved in my major, such as in machine learning models and in digital signal processing. For example, in my digital signals and filtering class, I got to realize how powerful eigenvalues are in signal filtering. So, see, I'm genuinely amazed at how powerful linear algebra is. So, this student really benefited, it seems like, doing this abstract course, but in her major. I recently saw her, and she said that she actually, I don't remember, she's adding math as a minor, or maybe she's double majoring in math, but that definitely had an impact on her. So this algorithmic structure, I thought that this would be a, not easy, but I was thinking that maybe this would be a good one for programming for students to get a handle on. And of course, this is not, the translation is not trivial. I knew that, but I wanted to just trial this. So we had a limited data. Caleb and I are analyzing the rest, and we have written almost the paper, but we think that a lot of students basically did well in translating this proof into the code. Uh, so we have more to say about this. So interestingly, that this entire process was kind of very based on an abstract idea. There's not whole lot of computation, numerical computation maybe, but not real computation. So we think that really added to the complexity of this process for the students. So I've taught this course before, like 6 times, and so these are my challenges as a instructor here, that the existing course is demanding. Is so many things you have to cover, and here I am trying to bring this more things in here. So like Hossein said, I did not grade the labs. Basically, it was based on completion because I didn't want to punish people for no good reason. I wanted them to have fun and enjoy and learn, mostly learn something new. If it wasn't because of the weekly meetings that I had with MathWorks personnel, I don't think I would have even tried this idea. Another thing I was going to say, that students don't ever underestimate your undergraduates, especially these days. The students are amazing and they can bring so much and they can produce really high quality work. So these students were mostly math majors, but also from STEM. So this semester, I'm taking a sabbatical, but during my sabbatical, I'm creating a linear algebra course again with a collaboration with MathWorks. So some people read this or see this and they think that, yeah, why didn't you include this and why didn't you do that? So it's not like this was not intended in the beginning to begin with. It was an abstract course, and I was just trying to basically trial some ideas in here. So here are some of our references, and thank you so much for your attention.
Okay. Thanks, Caleb. Thanks, Sepideh. Thanks, Sepideh and Caleb. Time for a quick question. Jim, yes, hang on.
Caleb will answer the hard questions, and I'll do the easy ones.
I hope Jim's got an easy one.
Oh, good.
Thanks, Sepideh and Caleb. That was really interesting. I just had a question about the student one and about their use of code well, this is a question really. to either exemplify or validate a result, or in their mind, to actually prove the result in full formality and generality? What were they actually thinking when they generated that code? Were they thinking that they generated a proof even though they're using randomly generated matrices, etc., or were they thinking that they were just coming up with a whole bunch of instances to show that the theorem works when you throw a bunch of random instances at it? Thank you.
Yeah, I'll let Caleb. Caleb is nodding, so you go first, Caleb.
So I do remember what student one wrote was that this demonstrates the theorem. So I don't think that they thought that this code was like an exhaustive proof, but I think it was meant to be this shows a lot of cases. And the student actually went very far to randomize so many aspects of the linearly dependent list that they were trying to create this as a very generic approach to the problem. So I'd say the latter case of what you were saying. They knew it wasn't an exhaustive proof, but it did demonstrate a wide variety of cases
Yeah,
as
I
far as
also
they
wanted
could perceive.
sorry. I also wanted to add that there were two students, not the student one, but there are two other students who were STEM students, and so they did not come from the rigorous, which is Jess's mathematics, did not come from that background, but they were amazing in coding. So these two students could not produce a proof in the midterm, but their actual codes were amazing, right, Caleb? The two students. So all of these students had the proof in front of them, and my goal was for them to kind of show and validate to me that this actually Axler's proof is actually does work. That was my intention.
Okay, well, let's thank Sepideh and Caleb again. Thank you.
Thank you so much.